Good evening, everyone. My name is Yong Hao, and together with Zhang Han, we'll be presenting on linear and logistic regression to you guys. All right, thank you very much for attending our workshop, and we will start now. So before we move into the main content, of today, I'll first do a brief introduction about MLDA. So MLDA at EEE is a student-centric lab which aims to provide a platform to empower our EEE or IEM students learning and deploying of machine learning and data analytics skills and knowledge in both academia and industry. We do so through our various events, projects, and activities. And as a student committee of MLDA, our mission to execute and plan those events and workshops. And how do we do it? We do it through the help of our state-of-the-art faculty, resource, and technical support to facilitate your learning journey in machine learning and data analytics, which is the hot topic of the decade. We also bring in knowledge and skills for machine learning through our 4 different pillars of events, ranging from our machine learning projects, industry projects, and career events and workshops with competition. All right. So for today's workshop, the linear regression part will be conducted by me, while the logistic regression part will be conducted by Zhang Han. All right. Zhang Han, you want to say something? Okay, yeah. So for these 2 parts, we'll be first covering theory, and then we'll be going through code in Google Colab. All right, so first of all, we'll be talking about what is supervised learning and what is unsupervised learning. So for example, you can think about something like when you have a question about if you want a model to predict whether some image is a dog or a cat. All right, so for supervised learning, you will give the model the input, which is the images of dogs and cats, and you tell the model what images are dogs and what images are cats. So that is supervised learning. That means you give the model the answers and you want the model to fit towards the answer. All right, but then for unsupervised learning, you are essentially throwing in all the images without letting the model know which are dogs and which are cats. So you are depending on algorithms that will make the classification for you by itself. All right, so this is supervised learning versus unsupervised learning. And so you can see that the process and input data comparisons are as follows, which are basically what I've said earlier. And linear and logistic regressions are both under supervised learning. That is, we provide the answers for the model and we expect the model to train to fit towards the data. Okay. All right, so the computational complexity is simpler for supervised learning and more computationally complex for unsupervised learning. That's because unsupervised learning depends on the algorithm itself to do the classification, right? And accuracy-wise, for supervised learning, it will be more accurate to some extent because you are already giving the answers to the model and you're expecting it to fit towards the answers, right? Okay, and so for supervised learning, your learning will take place offline. That means you train your model offline and then you deploy your model. Whilst for unsupervised learning, you're letting your model classify it real time. That means it won't have time to train and it just classifies on the spot. All right, so the number of classes for supervised learning is known and for unsupervised learning is unknown. That means you're allowing the model to determine how many different classes are there in your set of data. So that is the difference between supervised learning and unsupervised learning. Okay, so if there are any questions, you can type in the chat and we'll try to answer you to our best abilities. All right, so moving on. Okay, so I'll first talk about the supervised learning main pipeline. So back to the examples of images of dogs and cats. So let's say you want to train a model to identify dogs and cats. So first, what you have to do is you have to acquire the data first. So yeah, for example, you go to Kaggle or some websites, or you do some web scraping to get all the data, dogs and cats images. And then you have to do data exploration and preparation to know how many dogs you have, how many cats you have. And then we have to split our data for training and for testing. All right. So first of all, you have to split into the training data. Then you build your model with the training data. Okay. So after that, you can test your model with some other validation data. That means that if you have a bunch of training data, you won't use all of them to train. You will actually split like maybe 20% as validation data. That means this data will not be seen by the model yet. And when you do model testing, you can actually use validation data or test data, essentially. That means you have to keep some of the data and not let the model see them before you finish training your model, and then you test it on it. So if the results of the testing is not what you want, not as good as you expect, then you have to go back to training your model. Like maybe increase the number of iterations of the training, or increasing the data, or you have to do some data augmentation or something like that, so that you improve your model accuracy. And finally, you move on to model deployment. All right, so this is basically the whole supervised learning main pipeline. Remember, for supervised learning, you actually give the answers to the model already. All right. So moving on. So we'll dive into our first main topic today, that is linear regression. All right, so linear regression basically is just a straight line, as you know from the name linear. All right, so data is modeled with a straight line, and so it takes in continuous data as input and generates the corresponding output, which is also continuous data. Okay, what this means is that everything in linear regression is just numbers. So there will be a lot of floats and decimals, and it's just all numbers. You give the model numbers, it creates a line that will generate numbers back to you. All right. So what are some applications of linear regression? So you can actually just predict the outcome of political elections, like based on like past data. Okay. Then you can predict the behavior of the stock market based on past trends as well. So you can predict, okay, what is the price of the stock market today? What it will be tomorrow? What will it be in the next month? Or you can predict the performance of professional athletes given his training results based on his past experiences, past records, and then you can output your performance that you expect in a competition for an athlete. All right, or you can just do some correlation experiments. Right. So for example, you want to know what is the effect of a proposed drug on a patient in a control study, which means that you alter everything. You keep everything constant except for the drug doses or something else. Then you tweak the variable and see how it correlates to the effects on the patient. Okay, so these are basically some applications of the linear regression model. Okay, so simple linear regression. So there are some terms that you will have to know. Okay, so the first sentence is just is used to study relationship between two continuous variables, which are like both numerical variables, as I've explained earlier. So consists of one variable denoted as x, which is commonly called the predictor or the explanatory or the independent variable. Okay, and the other variable denoted as y will be regarded as the response outcome or dependent variable. Okay, so you can look at the table here at the bottom right corner. So let's say you want to predict the height of a person using the weight of a person, right? So the weight of the person will be the predictor, explanatory, or independent variable. Okay, so basically that will be your training data or your variables. Okay, and so your y will be your output, which is your response outcome or dependent variable. Okay, basically you train a model based on this. Okay, so both of these will be a set of training data. Okay, so that's why y will be the answers. Okay, so both of these will be your training data, and a set of x and y is regarded as a sample. Okay, but essentially when you are testing out your model or you are using a model, the only thing that you give your model is your X or your predicted explanatory or independent variable, or in this case, the weight. Okay, so you just give it that and it will tell you what is the height based on the linear regression model. Okay, something like that. Okay, so for simple linear regression, it is simple because it uses only one predictor variable. Okay, so in this case, the only predictor variable is just weight. All right. Okay, so let's just say that this is like this is the linear regression line or model for weight and height. So the same thing, we're using weight to predict the height, and you can see all these small dots here. These small dots here are just every sample X and Y that we have. Okay. Okay, then what you see in the center is actually the linear regression line. All right. Oh. Okay, so what you need to know is that simple linear regression model is something like this equation. Okay. So what you have here is Y, which is the output that we have talked about just now. And then you have X, which is the predictor variable. Okay. Then you have B1, which is what we call the weight or the gradient. Okay, so it's called weight because it's directly affecting the weightage of X1. Okay, or what you call the predictor variables. All right. Then we have B0, which is the bias or the y-intercept. Okay, this is just like a straight line when you graph y equals to mx plus c. Okay. Then you can see the error. There's an error term. Okay, so this error term is actually something that is not really related to simple linear regression. What it means is just this, if there's an error, it is like you can't really improve the error by tweaking your weights or bias parameters. It simply means that sometimes this data is just not fit to a simple linear regression line. So this is the error. All right. And yeah, so basically when you have all these set, then what you have is an estimated simple linear regression equation. So this is what our final model looks like, which is basically this line here in the left graph. All right, so yeah, you'll be using this to output your y or your response variable. Okay, so whenever you put x, then you get your y. Okay, no drawings. So how do we fit the line? Okay, first we will need to have a cost function, which is the error function, or how do we know how far are we from fitting it to the real line or the ideal line that we want. All right. So how do we do that? We basically do that with some squared error. You notice that there's some dotted lines here from the sample to the model here, and this is the error. Okay, so what we do here is we take the squared error, which means you take this error and you square it. The reason that we do that is to not let the errors cancel themselves out, because you notice that some errors are actually negative. For example, like this one here. Okay, so we have to take the squared error to account for all the errors along the graph. Okay, so that's why our loss function is squared error and not just the error. All right, and then for cost function, which is what we'll be using to optimize our model. Okay, you will need to average it over all the training samples. All right, so this is the loss function. Okay, so when you minimize all these errors to some point, it will be your ideal best fit line or your simple linear regression model. All right. Okay, so so there's actually some formula that is already been tested out by a lot of like data scientists or mathematicians, and they figure out that this is how you can get the linear regression model with just formulas. So we can just remember this equation is just the least squares the squared error equation, where this is actually your model, your y prime. Oh my god, okay. Then you can just take the derivative with respect to b naught and b1, okay, and set it to 0. Okay, this specifically means the partial differentiation with respect to b naught and b1. Okay, then you solve for b naught and b1, then you get the least squares estimates. And you notice that these are just two formulas that we use to solve for the least squares regression line. Okay, so this is by empirical, or okay, they basically test it out, and this is actually the formula. Okay. So what a very common algorithm does is it uses the normal equation. Okay. So you don't really need to know how to compute this. Okay, you just need to know that this is how one of the Python libraries, the sklearn linear regression model, computes its gradients, right? Like for each of these parameters. So this is already like the optimized parameters, okay, the data. All right, then you notice that there's transposes and some matrix multiplication and some matrix inversion. So what you need to know is that this is kind of an efficient way because it's already in matrices, and the sklearn library actually does very well or very efficiently calculates things when it involves matrices. Okay, but it will only work well with small features. Okay, which means there's not really a lot of samples, and there's not really a lot of different variables. Okay, because it involves matrix inversion, which is, if you know the big O notation, and cube, which means that if you scale your data samples twice or you double the number of samples, then the number of operations increase by 8 times. Okay, so this is not really scalable, and especially if you're dealing with large features, that means features that have a lot of samples or a lot of different variables, okay, which will increase the size of the matrix. All right. So yeah, this is the normal equation. So what can we do? We use the gradient descent algorithm. Okay. Okay. So the benefits of using the gradient descent algorithm is it is an ON function. Okay. What it does is, let's say this is your loss function, okay, and you have your initial position on the top part of the graph. Okay, so what it does is it just keeps on going down until you reach the minimum point, which will be your final position. All right. Okay. So how does this gradient descent algorithm work? Okay, you remember this cost function here. So what we do is, basically minimize this cost function with differentiation, equating it to 0, and you get a minimum, etc. Okay, so and see that we take the partial derivative with respect to b1. Okay, this is how you do it. Okay, then you notice that there's a coefficient half here. Why do we have the coefficient half here? Is because when you do differentiation, you bring down the 2 power 2, and it will cancel it out, making your calculations more efficient. Essentially, even if you don't have the half there, the model will work fine. Okay, so this is what you get for your gradients. So this is basically some gradients for db1 and gradients for db0. What you have to do is to update your steps or your b1 and b0. Okay, so you have your L as a learning rate, okay, which is basically a constant, how much you want to scale based on the gradient that you got, okay, with your b1. Okay. So I can explain it here. So let's say this is what you are doing. So what your graph looks like, your cost graph, and you have your loss here, and you have your weight of bias here. So what we do with partial differentiation is we basically, let's say we are doing it with respect to b1. Okay, then we have your b1 as your x-axis variable. Right. Then if your initial position is here, okay, then what you get for your gradient is actually this, right? Then you will get a positive gradient. So what you do is you minus this gradient with a constant. So yeah, if you remember, okay, so positive gradient, and for now your position is here, right? Okay, this is your B1 position. So if you minus a positive number, then you get a less positive B1. Okay, that's why you are here. And then you just repeat until you get to the final position where your gradient is very, very small and it basically bring you to the minimum. Okay, so the same thing will happen when your initial starting point is actually on the left side of the graph, okay, where you get some negative gradient. And when you subtract your negative gradient from your initial B1 position, you actually get a more positive B1, okay, which will bring you to the right and then slowly move towards the final position. Okay, so that is actually how gradient descent algorithms work. All right. Okay, so what you have to note for some gradient descent algorithm is the learning rate. Okay, so if your learning rate is too small, then it will take very, very long to converge and it will converge very slowly. Okay, so this will work if you have a lot of time and you are very patient and you just let your model train all day, all up until it reaches the minimum point. Okay, so that is not really efficient and that is not really what we want. Okay, and it cannot be too big as well. The reason being, if it is too big, then even if your weight is already like near the minimum, when you add on the gradient or you subtract the gradient, then you just overshoot. Okay, they overshoot, then it gets a larger gradient, then it continues to overshoot, then it just diverges. Okay, so that is also not what we want. So we need the optimal learning rate. Okay, so the gradient descent algorithm will be used in a lot of different models. So this is some introduction for you. Okay, so it's not only used in linear regression, it will be used in a lot of regression models. Okay, this is to just a way to minimize your cost function. So next we'll talk about convex and non-convex functions. Okay, so what is a convex function? So in a convex function, your local minima will be the same as your global minimum. Okay, so what it means that if you see the convex function here, there's only one minimum, and that minimum is both your local and your global minimum. Right? So if you have a non-convex function, then you have many minimums, and there'll be only one global minimum. But then the minimum that you get, like let's say with a gradient descent function, is not necessarily your global minimum, and it might be your local minimum. And in which case, your model didn't really reach the optimal point. All right. Another thing about the convex function is that if you draw a straight line between any 2 points on the graph, then it will lie above the graph. Okay? And it does not intersect the graph other than the 2 points. Okay, so this will happen nicely with a convex graph, but this will not happen nicely with a non-convex graph. You see that it can intersect more than 2 points. Okay, so the idea here is the gradient descent, okay, or any other optimization algorithm is guaranteed to find the minimum only for convex functions. Okay, if the learning rate is not too large and you went through enough iterations. Okay, so but you not have to worry about this here, because linear regression and logistic regression will model your function so to make it look like a convex function. That means it will always be able to find the minimum with gradient descent. All right. Okay. So next we have a multiple variable linear regression. All right. So it's an extension of simple linear regression where 2 or more predictor variables are used to predict the variance of one response variable. So, okay, let's say that you are predicting the house price, okay? And if you are just using simple linear regression, then you might just be using this part of the data, okay? So you'll be using your house location to predict your house price. which is not really accurate, as you know, because not every location only has like one house price. All right, so you know that that's not really enough. The data is not sufficient. Okay, so what you need to do is you need to use the whole data set here. And how do you do that? You do a multiple variable linear regression. Okay, so all these, the house size, the house age, and the house locations are all variables that you will use to predict your house price. Okay, and you notice that the model itself is not really that complicated because it's just more our weights and more variables added together. And it's essentially the same as the simple linear regression model and a simple linear regression equation. And basically what every one of these variables mean is that, okay, so let's say you have a gradient for x1, which is a b1, beta 1. Okay, so let's say the gradient is like maybe a 2. So it just means that whenever a 1 unit increase in x1 will be a 2 unit increase in y. Okay, so each of the variable will have a meaning similar to that. Okay, so this is essentially what the multiple linear regression model equation is doing. Okay, and if you have only 2 variables, then you can look at your right here. This is what the model will like. Essentially, it will look like a 3D plane. Okay. Okay, and one more thing you have to note is how the Python libraries does all these modeling. Okay, so basically they do vectorization. Okay, which means that they make all your inputs into vectors, and then they do some multiplication dot products or something like that. Okay, so you notice that there's a transpose. So what this transpose does is it just brings down all your variables into b0, b1, b2, dot, dot, dot. So this is the transpose one. Then you have your x0, x1, dot, 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 dot. So this will multiply to this one. This will multiply to this one. This multiplies to this one, so on and so forth. Okay, but then you notice that in our equation, our x0 is actually, there's no x0. Well, so what that means is that you just need to put x0 as 1. Okay, so that's actually what the machine is doing behind the scenes. Okay, so why do we have to vectorize? It's because if you use for loop to add on all these variables, then it's very slow in Python, right? And the vectorized code, okay, use highly optimized linear algebra libraries, which is in Python. There's a lot of libraries for machine learning purposes. And matrix multiplication is very fast on graphics processing unit. All right. So this is why we have to do all this, or they have to do all this. We are just the users. Okay. So some potential issues with multivariate linear regression. So 2 problems may arise. One is that you may overfit if you have too many predicted variables that account for more variance but do not add value to the model. What this means is that, okay, let's say you want to predict some output, but then you have like 20 different predicted variables. Okay, so some of them may correlate, some of them don't. Okay, but then what it does is it eventually overfits your model, which means that your model just fits towards this type of data. Okay, when there's a more general data, your model will not be able to predict correctly because there's too many variables influencing its decision. Okay, so the next thing is multi-collinearity, which means some predicted variables correlate with each other. Okay, so the problem with this is that you don't really need 2 variables that is like correlate with each other because it will make it difficult for you to know which variable is actually affecting your model. Okay, and it doesn't really add a lot of value to the model at the same time, okay, because they correlate to each other. Right. So the ideal is for all predicted variables to be correlated with the response variables, but not with each other. Okay, so the last thing you need to note is the evaluation matrix for linear regression. Okay, so this is different from the loss function or the cost function that we talked about earlier. And the cost function is for the model to optimize itself to get the ideal model. But the evaluation matrix is for us to test the model. So remember the pipeline that I have mentioned just now. Okay, the last step is to test before you deploy, right? So what we need is okay, so these are just some metrics for you to evaluate the accuracy of your model. Okay, so the mean absolute error, okay, is just okay, you just take the modulus of your original data, the actual value, going minus your predicted value, and you divide by the number of samples. Okay, so this is one metric. Okay, the problem with this is that it does not punish large errors. Okay, what does it mean? Okay, if you look at the mean squared error below, okay, every error that you have is squared. Okay, that means the larger errors are noted more. All right, then your model will do more work to actually optimize your model towards a lower error. Okay, so that's the benefit of using a mean squared error. Okay, what about a root mean squared error? Okay, so the reason people use root mean squared error over mean squared error is because root mean squared error actually reduces the squared error back to the initial units, which is the same as the unit sy. Okay, that's the reason for using root mean squared error. Okay, so there's another even more common score that is used very frequently in evaluating a model. That is the R2 score, which is this formula here. And basically what it does is it will get a percentage. Okay, so people like this score because it just shows, okay, how good is your model based on the percentage. So like 90% accurate, 80% accurate, 70% accurate. Okay, so that's what the R2 score will output for you. Right, so these are all the evaluation metrics, or not all, but commonly used metrics for linear regression evaluation. Okay, so you must take note that evaluation of error should consider context. So what this means is that if you get a root mean squared error of $10 for your models, you have to know this $10 signifies different, it signifies, gives a different meaning. Okay, if you're training a model for different things. For example, $10 loss for a candy bar may be huge. Okay, so for the price of a candy bar. Okay, but then a $10 loss for a house price may not be that huge, and it may be considered very good. Okay, because a house price is normally like 100,000 or like 1 million. Yeah, so $10 is nothing. Okay, but yeah, that's basically what it means. You need to know your context when you are evaluating your model. Okay, so that's it for my part. Okay, now I'll proceed to the code. I'll send you guys the notebook. All right, so I send the link to the notebook here. Okay. So if you open your notebook, you should see something like this. Okay, so what you have to do here is first you have to save a copy in Drive. Okay, remember to save a copy in Drive and open a copy. Okay, so because you won't be able to edit here and save your progress, so you have to save a copy in your Drive first. Okay. Okay, I hope everyone is able to open the notebook. All right. Okay, so let's start. Okay, so for all your machine learning projects or whatever, you need 4 essential libraries. So I hope you all recognize what these are. So basically, pandas is for numerical computations in Python. NumPy is for to process your data with arrays, NumPy arrays. And then there's a matplotlib for visualization, and C1, which is an even better visualization library compared to matplotlib. Okay, so these are 4 libraries that you have to use most of the time. Okay. So just import these libraries. Okay, run this cell. Okay, yeah. To run cells, you can just click Shift Enter. Okay, then you proceed to the next cell. Okay. Yep. Okay. So for the first thing that I'll first cover some introduction to this simple linear regression, SGT regressor things, and then I'll go through another full pipeline with you all. Okay. So the first thing that we'll do is we have to get the MBA players dataset, which is what we'll be using for the moment. Okay, so you can either go to Kaggle to download if you have a Kaggle account, or you can just go to this quick download link, okay, which will bring you to this CSV file here. And what you need to do is click download, right? Which is basically download the file for you. Okay. Yeah, I hope you are able to download this. Okay. Then what you have to do is to run this cell and then choose file. Yeah, you have to basically search. Your file should be in your downloads folder. Okay, then you just click all seasons and then open. Okay, then you take some time to upload. Of course, there's more than one way to upload files to Google Colab. Okay, so this is just one of the ways that you use this code. So the other way is maybe to mount your Google Drive, your whole Google Drive, if you have your files in your Google Drive. Or you can take a look at this sub tab here, where you can do upload, and you can upload the session storage. Okay, so hope all of you are able to download and upload this to your Google Colab. The next thing that we will do here is to read the CSV file. Okay, notice that there's a path here, and how do you get the path? You actually can just go to this thing here, then say copy path. It should give you this. Okay. Yeah. So when you run this, you see the first 5 columns because it's a df.hit. Okay. Then what we'll do first is to analyze whether the weight of an NBA player is a good predicting factor of the height of that particular player. So just a very simple model. Okay. So we first declare our simple df, and what we do is we take a subsection of player weight and player height, and then we call simple df again to see what it looks like. All right. Okay. Then here is the formula, which is what I actually went through earlier. And you see this is the x values, then this is the y values, which are actually brought into arrays. Okay. Then you get the mean for x, the mean for y, then you get the length of x. Okay, so whatever this is, and then you can just do a for loop, which is the so this will get you the numerator, which if you remember, is just the multiplication of these two things and the denominator. Okay, then you perform a summation for all your data samples. Okay, then you get a B1 by doing this, and you get a B0 by doing this. Okay, which is just the equations that I flashed just now in the slides. All right, then after you're done with all this, then you get this, which is the coefficient and your intercept of your linear regression line. All right. So yeah, basically that's what the formula does. And if you plot this thing here, yeah, and you'll see, yeah, this is the red line is your regression line, and the black dots are and your blue dots are all your data samples. Okay, so the next thing that we'll do is we'll just import linear regression model from Succulent library. So you can click on these links, which will bring you to the documentation. If you want to read more, you can do so. Okay, so okay. After that, we'll just train the model. So this line might not apply every time. It just applies for this case because our array is one-dimensional, and to fit into the linear regression model, you need a like two-dimensional array. Okay, so this is basically just shaping, so it's a two-dimensional array. And then we can just instantiate the linear regression object, and we fit the object, yeah, to your data points. Okay, so you just fit, and then you can see that the coefficients are exactly the same as the formula. Boom. Okay, yeah, that's why they are actually doing like the same stuff. Okay, and then there's also a built-in function in this regression model from scikit-learn. And if you run this, it's essentially doing the R2 score function for you, which will give you a 0.68, like 68.9% accuracy or something like that. And then you can plot the heat maps as well, which will give you the correlation between play weight and play height. And you can see that the correlation is quite high. All right, so that's basically how you train a model with simple linear regression from scikit-learn, okay, or using the formula. Okay, so the other way that you can do this is using the SGD regressor. And you notice that this is just the application of gradient descent algorithm. Okay, but what is different is there's a stochastic word, and the stochastic just means that instead of running the whole batch of data samples through a gradient descent, because sometimes you have like 1 million or 100,000 or a few 100,000 data sets, and you don't really want to run the whole batch into your gradient descent and expect it to actually compute your gradients and minimize your cost functions and whatever, because it will take a very, very long time. So stochastic is actually some tool a way to actually just randomly sample some data points and compute the gradient based on that batch of that sample of data from your whole big pool of data sample. Okay, so that's what stochastic gradient descent means. Okay, so what we do is we just import it from SGD regressor. And the problem with SGD regressor is you have to do a bit of a parameter tuning. Okay, so you notice that the ETA0, this is basically the learning rate constant that we talked about just now. And if you leave it as a default, it will be quite high, like 0.01. And if you leave it at that, the model will basically maybe diverge or just overshoot, and it will not result in very good results. Okay, verbose equals to 1 is just whether you want to show the training process. Okay, the max iterations is how many iterations do you want the model to go through. And there's actually a stop parameter that basically stops after a few iterations if the model doesn't improve, but I won't actually tune that here. Okay, then you have the learning rate adaptive. This is just one of the ways that to tune the training process. Okay, so there's a few ways to actually adapt your learning rate to make it string when the model is close to its minimum point. Okay, so adaptive is just one of them. So maybe after a few iterations where it doesn't improve, you just divide your learning rate by like 5 times. Okay, so yeah, if you run this, okay, you just instantiate an object. Okay, remember, you're just instantiating an object. It's called SGD-reg. Okay, then one more thing that you have to do is you have to scale your data. Okay, why do we do this? Because the SGD regressor is quite sensitive to some scaling. Okay, so if your model like is not scaled, and I don't know if it states here, it states somewhere in the documentation, okay, that is very sensitive to data size and scale. So you have to basically scale it. And how do we scale it? We do some standard normal distribution thing where we get your Z value by subtracting the mean and dividing by the standard deviation. Okay, so when you do okay, so you have to call this scalar thing first, then you feed to your X data, then after that you transform them. Okay, so yeah, when you feed, you get all your mean and standard deviation, and then you can just transform your X after that and get the X scaled. Okay, then you can just feed it. Okay, it's the same thing. And you see that all these training progresses. Okay, and you see that it's like 590 epochs and it's not 1000. The reason being, yeah, just stop after a few epochs that it's not really improving. Okay, then we can print the coefficients. Okay, then you notice that these are not the same because we actually scaled the trained data. Okay, then we cannot really compare them with the previous models. Okay, when you look at the score, yeah, you see that it's almost the same. Okay, so a lot of that's why the linear regression model from Succulent is more commonly used compared to the SGG regressor, because in most cases your data won't be really large, in the sense that it will actually fail your linear regression model from Succulent. Okay, and actually if the inversion matrix function is too complicated for Succulent to perform, it will actually give you a warning. Okay, and in most cases you won't reach that stage. That's why a lot of people just use linear regression instead of using SGG regressor. All right, so in the rest of the notebook, we will also be using linear regression model only. Okay, so what we'll do next is we'll just predict the player height, but then now we'll add another variable. Okay, this variable is called rebound. Okay, so like, because it's the NBA context, which is the basketball league context, so rebound is basically when the ball is shoot towards the rim and the frame, and it bounces back and the player catches it. Yeah, that's the average rebound. Okay, if you want to know more about what each variable mean, you can refer to the top of the notebook. I actually copied all the meanings of the variables there, and you can feel free to play around with them if you want. Okay, so we'll create a subtable with these three variables. Okay, player height is our output. Okay, you can do a describe and you will see what are the min and max, whatever. Okay, then this is just reshaping, okay, to make it two-dimensional. Okay, then yeah, same thing here, import linear regression, instantiate the model, fit the model. Okay, and then you'll notice that there are now two coefficients instead of one. Okay, that's to account for the added variable that we have here. Then you can see the R2 score. Okay, and you notice that there's a slight improvement, 0.69 compared to 0.68, which you see earlier. Yeah. Okay, so yeah, that's the reason for adding more variables to your model. It makes the model more robust and makes it kind of more accurate in a sense. Okay, if you see here, it's not really a very highly correlated variable, but it works. All right. So the next thing here, you don't really have to worry about. You just have to run the code. You don't really have to worry about this. Just run the code, because it's just to show you guys what the plot looks like. Okay, so you can see here that the black dots are actually all the data points, and the plane is actually your model. Okay, the blue plane, and these are like three angles and elevations that shows you like different perspectives of the model. Okay, so next we'll go through a full pipeline walkthrough. Okay, so yeah, import the libraries as well. Notice that there's a matplotlib inline. Okay, so the next thing that we'll do is to predict housing data, okay, based on the data set. Okay, the same thing that you have to do here is to do a quick download from this thing that I saved in the Google Drive. Okay, hopefully you can download this data as well. All right, then you have to upload it again back to Google Drive. Yeah, KC house data. Okay. Yeah, notice that it takes quite some time to load because there's actually a lot of data. Okay. Okay, yes, finally done. And then the next thing that we have to do is read the CSV, get the head. And these are just some things that you can do, describe and info. So this is for you to check the min max. This is for you to check if there are any null objects or any objects which are like missing columns or missing rows. Okay, then the next thing that you can do is to do a isNow.sum again. Then you notice that, okay, there's nothing wrong with this data. And you don't have to fill any of them with means or modes or anything. So that's basically what you need to do when you first get your data for your machine learning projects. Okay, so what you have to do here is we have to filter out some variables that are not really useful for linear regression. Okay, so the first two that we can look at as is the waterfront and the view. Okay, because these are discrete variables, which means that they have discrete values like 0, 1. Okay, waterfront, yes or no. Then view, rating, 0 to 4. Okay, so notice that these are both like discrete variables. And then you can visualize your data. Okay, so this will require you all to follow through a bit. Right, so first we have to plot our heat map. Okay, so what I need to do here is to do these two lines are actually just setting. This is set to set figure size, and this is to round all your data to 2 decimal places. You know what I mean in a while. So heat map data equals to correlation matrix, which is what we made here, and then n0 equals to true. Okay, so n0 just means that you annotate your data, and then yeah, you'll see that all of them are 2 decimal places, okay, because you rounded them. Okay, so basically what this heat map does is it shows you which data correlates to each other better. Okay, in this case, we are going to look very closely at the price one, at the price row. And what we do is we have to filter out all those that has correlation coefficients less than 0.1. Okay, so before that, we can take a look at the view and the waterfront plots, okay, which is basically doesn't seem like a linear regression model. So yeah, we're gonna get rid of them. Okay, so what we do is we just drop all these that actually have correlation coefficients less than 0.1. Okay, drop all of them, remember to put in place equals to true, and move on. Okay, so next thing we have to clean our data a bit. And what we'll do is we'll use the box plot theories. Okay, so if you plot all the different variables here, okay, yeah, this is just the syntax for plotting box plots. Okay, then you notice that there's a lot of outliers. Okay, these are all outliers, these dots here. Okay, basically we will remove them. And how do we remove them? We just take the ones in the interquartile range and remove the rest. Okay, yeah, then you will just run this. So, and then we run a for loop. Okay, we get the quartile, the first quartile, the third quartile, get the interquartile range. Then we set the lower limit on the upper limit. And then we just run some code where it's more than upper limit, then we just remove them. Is less than lower limit, we just remove them. Okay, so this is the code. And then after that, you can see that it is now clean. Yes, okay, yeah. And after that, we will proceed to train our model. Okay, so yeah. Okay. Not sure if you guys remember the syntax, but yeah. What you have to do is for this one, for our x1, you have to drop price. Okay. Okay, x is equals to 1. Okay. Then we do a y, okay, which is our output variable, and we do df price. Okay. Oh, okay. Let's put this here. Okay, then we perform a train test split. Okay, so we import train test split. So basically, this function does automatically split your data into train and test data or validation test data. Oh, sorry, yeah, test data that you use for your training. Okay, so you have X train, Y train. Sorry, let me syntax properly. Sorry, X train, X test, Y train, Y test equals to train test split. X, Y, okay, test size equals to 0.2. So basically what it does is it sets 20% of your train data as your test data. Okay, 20% of your whole data as your test data. And then we have your random state equals to any number you like, 21. Okay, so the reason for doing random state 21 is just to make sure that every time you do this, it will be the same set of data that will be your train data and the same set of data that will be your test data. Okay, so you can also don't use this if you don't want to keep track of how your data is being split. Okay, and you actually don't have to memorize this as well because you can just go to documentation and they'll have the syntax there for you. Okay, then after that we do the scaling. Okay, so we have scalar equals to standard scalar. Then we have X train equals to scalar dot fit X train. Transform X train, Y train. Okay, then we do a similar thing for our Y test. Sorry, X test. Oh my God. Okay, so realize the first one have fit because you want to find the first part you want to find the mean and the standard deviation. That's why you need a fit transform. Now for the second part, you are just doing a transform because what you're doing is you're essentially applying your mean and standard deviation to your X test as well, but you don't do that to your Y test. Okay. Then next thing you just have to instantiate and train. Okay, so lean rec goes to linear regression. So lean rec dot fit X train Y train. Okay, that's what you need to do. Oh, sorry. Oh God. Oh God. Okay. Then we train. Okay. After that, we have to make a predictions with our model. Okay, so now we've done training our model. We have to predict and evaluate. So what we do, get predictions, goes to lean rec dot predict Y train. Oh, sorry. Yeah. Yeah, linear.predict access. Okay, and you can actually see what are your predictions, which actually looks like this, which is a whole lot of arrays with a lot of numbers, okay, which are like your house prices, right? Okay, so the last thing that we need to do is to evaluate whether this model is accurate or not, right? So Succulent actually also have all these ready for you. So you can see the SR2 score, the mean squared error, and the mean absolute error. Okay, so what you need to do is just to import them. And then when you run them, you just run mean absolute error. Then you do a y-test and your predictions. Okay, so basically you are using your y-test and your predictions in your evaluation matrix, which you remember these are the two variables that you need based on the slide that I showed just now. Okay, and notice that there's root mean squared error. So how do you calculate that? And Succulent doesn't have a root mean squared error function. Okay, so basically what you need to do is just use NumPy. Then you do np.square root mean squared error y-test and predictions. Okay, then we're done. Oh, okay. Oh, hang on. This is not really right. Test predictions. Okay, so yeah, basically this is just how you can do all your. Okay, this is basically the full pipeline of training and testing your linear regression model. Okay, so there might be something wrong with the code that I typed just now, okay, but I'll figure out later. Okay, but yeah, so that's basically it for the linear regression part of the workshop. And now I'll pass the time to Zhanghai. Okay.
Okay, let me share my screen. Okay, hi guys. Congratulations, you have now understand the linear regression. And don't worry if you have any problem. Later we will type for you to ask questions. And now let me talk about the logistic regression. Okay, first let me have a brief introduction of the model. Although this model is called logistic regression, but in fact, it's not a regression model. It's a classification model. And usually, it's used for two classifications. And now it's widely loved by industries because its simplicity, parallelization, and strong interpretability. And usually, we use the logistic regression to predict, for example, the factors of several of centered diseases to say if you have a feature, the probability to get the diseases. And before I further explain this, let me provide you some background information. The first is that I just told you this is a classification model. So what's the classification and the regression tasks? In fact, we have two types of problems. One is the regression problem, and another is the classification problem. For the regression problem, the inputs and output variables are both continuous variables. As shown in the linear regression, you say in your house model, both the x and y are continuous. However, for the classification model, our input variable can be continuous, but the output variable is a finite number of different variables. For example, we usually use the logistic regression for two classifications, which means if we give an input, then the output should be either 1 or 2. 1 means a category, and 1 or 0, and 0 means another category. So therefore, we can use this classification. And also, both the linear regression and the logistic regression can be grouped into the generalized linear model, which is short for CLM. So what's the difference between the linear regression and the logistic regression? This is because they have the different distribution of data. For the linear regression, it's usually continuous. For logistic regression, they have we assume the data to have a binomial distribution. And you see there are other types of regression. Similarly, they have different distribution of data. For example, the portion regression is usually distributed similar to the portion, follow the portion rules. And the negative binomial regression usually has a negative binomial distribution. And on the right, you say I put a picture here. This shows the binomial distribution of the logistic regression. You see, it's very similar to nominal distribution, right? But there's some difference. For binomial distribution, it has a higher peak and longer tails. So if you explore the data and say that it has long tails, then probably you can use the logistic regression. Till now, I have explained the basic idea of logistic regression. What you need to remember is just the essence of logistic regression, which are listed here. Only 2 points. First is that we assume the data obey the binomial distribution as I explained earlier. And then what we do is to use the maximum likelihood estimation to estimate the parameters. I will explain this later. Okay, and now I still have another concept to introduce, which is the decision boundary of the classification problems. As you can see, there are 3 pictures I put here. They all have lines to separate the to divide the plan into two areas, and for this different area means a different category. We show this as green and red. And for logistic regression, it usually have this picture. This is a very simple and basic concept of the logistic regression, which we can say the strict line here. And according to mathematics rules, we can express the straight line, use this expression. You just need to remember that for this expression we have the parameter theta, which we need to solve later, and also the x is the input. So now, let me explain the pipeline of logistic regression to make you clear how the logistic regression works. So basically, we have 3 steps. The first is to find the H function, which is a hypothesis. And the second, we construct the J function, which is the loss function. And finally, we find a way to minimize the loss function and obtain the regression parameter theta. For the H function, in the logistic regression, we use the sigmoid function, which is also called the logistic function or the logistic function. And this is the activation function of logistic regression. And what's the feature of it? I already showed us this picture. You see we have the input, and then we get the output, which is bounded by 1 and 0. And 1, 0, you remember, that's the output we want. So how we get the sigmoid function is just from the linear expression we say before, which is constructed by theta and x. So we just substitute this linear expression into the function and we got this. This H is the hypothesis function we will use to predict later. So what's the role of the H function in logistic regression? It's not like in the linear regression we use. In linear regression we use it to predict the value, but in logistic regression we use this to predict the possibilities. And I show this as here. We can get the possibility for y equals 0 and y equal to 1. Okay, just now is the H function. Now we come to the J function. In this step, we will compute the loss of our expression. The process is just mathematics, so I don't need to explain this. I just show the result for you. This is a cost function we will use to compute the error between the actual value and the prediction. And finally, we come to the last step, which is to find a way to minimize the J function and obtain the regression parameter theta. Now, here I will explain one way, which is called gradient descent method. I believe that you already heard this in the linear regression. So I'll just simply explain it. The goal of using this gradient descent method is to calculate the theta. We get the value of theta such that we got the minimum value of cost function. And the process is like this. The top equation is how we update the theta. And the below is the process how we got this. And just I say that we need to find a way to get the minimum cost function. So which means there are other ways to get this. And I list some ways here. you can explore this later. All these have different strong points and shortcomings, which you can choose in different situations. So till now, we say we have constructed the H function, the J function, and also we minimized the cost function, the value of cost function. Now what we get is we get the value of theta. You say we solve for the value of theta to get the minimum value of the cost function, and we use this theta so we can compute, so we can get this line. This is the line we predicted, and use this line we can classification our data for like this. And also here is the H function. You remember, if we got theta, we can also compute this H function. What this H function means, I explained earlier, is that the possibility of the results, whether it's equal to 1 or equal to 0. The above is just for the two classification application of the logistic regression. But logistic regression can do more things. For example, the multi-class classification problem. And the idea of this multi-class classification problem is that we can first compute at each point. For example, here we have 3 categories, and at each point we can compute the possibilities of these 3 categories. For example, at a point here, we compute for the green, there's a possibility, and for the red, for the blue, there's a possibility respectively. And we compare the 3 possibilities and get the maximum value. And this is, and the maximum value will be our final classification of this point. Here is the expression. We only care about the max value of the H function at this point. Okay. We have gone through all the pipeline of logistic regression. And now I need to have a extension of why we combine this linear regression and the logistic regression here into one workshop. This is because there are some internal link between them. For the linear regression, we get the linear expression, and the data has the nominal distribution. And for logistic regression, we also compute the linear expression first. You remember, and then we have another step, which is to compute the possibility, which is called the H function. And for logistic regression, we obey the binomial distribution, and here is the Burr distribution. And the Burr distribution and the binomial distribution is the same thing. So the difference between the linear regression and the logistic regression is that we have another layer, which is to link the linear expression with the possibility distribution, which is the H function. So I introduced before is that both the linear regression and logistic regression belong to the generalized linear regressions, and there are specific terms for this. For the linear expression, it's called the linear predictor, and for the H function, it's called the link function. And also there's a possibility distribution. Okay, I think that's all for the logistic regression. And next, I will talk about the code. So at first, I will have a brief explanation of the code, and then I will send the code to you so you can look at it by yourself. For the code part, I just prepared a simple one so everybody can follow it. First, we upload the data set. Okay, so let me explain the next step. We import libraries here, and there are several libraries, but you just need to remember few of these. For example, we use a matplot plot to visualize our prediction. And we get the train set split to separate our train set and the test set. And also we use the logistic regression. This is the linear model. And for the logistic regression model, how we measure the performance, we introduce another function which is called accuracy score, which is imported from the scalar matrices. Okay, let me import the. So after we import the library, the first thing we do is to explore the data. We say, we read the Csv file and got these things. We have the age, the salary, and the purchased. The purchase means whether the person purchased the insurance. And there are other columns we do not need to care them. So for this data set, what we want to predict is that we use the age and the salary to predict whether this person purchased the insurance. And before we start prediction, we first look at the I have the exploration of the data set. So here we plot the purchased, the person who purchased the insurance and the not purchased. This is shown here. And then what we do is to separate the data into the train set and test set. Here we use the number 0.2 means the ratio of the train set and test set. Then what we do is to scale the train set and test set. Why we need this? It's because the raw data in the train set and test set, they have large range. And if they have large range, for the model to predict, there are many steps of gradient descending, which is to just minimize the range of the data. So that's not efficient. Instead, what we do is to we scale the data first. So the data are all normalized into the range 0 to 1. So for the model to predict, you will be much more efficient. So after the scaling, what we do is to predict. The prediction steps are very simple. Before you say, we just explore the logistic regression function. And here we just fix the tree set, and we just fit the data set to this model. So this function can predict it for us. So after the prediction, we will see whether this model performs well. Here we use the accuracy score function to test this. And you say the result is 0.925, which is quite good. So the most important steps are done. What we need to do next is just to visualize the predictions. Here, I just use the matplot library pyplot to predict this and print it as this picture. In the x-axis, we have the age, and in the y-axis, we have the estimate salary. And the color of dot shows that whether it purchased the insurance or not. This is, you see, this is for the this is for the test set. This is for the training set. We first train the model, and we got the data. Then we use it to predict the test set. And the result of the test set is shown in this picture. We also say that the performance is good. Okay, so as the code I provide you is quite easy, so I won't do it step by step. What I want to do now is to summarize how we implement the logistic regression. So first we get the data set, we import the libraries, and the function we use for prediction is the logistic regression function. And we export the data. Here is the steps you need to remember, which is very simple. You just need to scale the data first, and then fit the data into the model, the logistic model we introduced before. And then we predict and then we measure the performance of the model. And the last step is to visualize our results. Also, you can see that for the linear regression and the logistic regression, we use different ways. For example, Yonghao used the another way to test the to show the performance of the of his prediction. And here I use the accuracy score. So it's up to you to explore more. And also, what I want to say is that for the logistic regression and the linear regression, there are many similarities. So if you, for example, you want to use the functions which is already there are many things already blended by your house, so you can refer to this. Also, I have I will provide the extended reading materials to you. So if you want to explore more, you can read this. What I will do now is to share the dataset to you so you can try it by yourself. So everyone got the data right. Until this point, our the main content of our workshop is already explained it. So what we continue next is that if you have any questions, you can ask us now. And here is the feedback of our workshop. We really value your feedback.
Okay, then I would like to add on something. So just now the error is due to the scaling part. So if you run the code one more time, then you will not see any errors and you actually get this, which is actually some logical prediction scores. Okay. Yeah, that's it. Then, yeah, remember to leave us some feedback and we hope to improve here with your feedback. Okay. Thank you very much for attending and good night.